Here we're going to look at the meaning of domain and range. Let's start graphically. The domain represents all input values or x values of a function, whereas the range is all the y values or output values. Here's an example. Suppose we were asked to find the domain of this function. First, some things to note. This open circle means that that point is not part of the function, or that the function does not contain 3, 2. This arrow not only represents that the graph goes up forever, but it also represents that the graph goes leftward forever. And so keeping that in mind, let's think about what the domain of this function would be. The domain is all possible x values. Unfortunately, there's no procedure to find domain. And so what you have to do is you have to just be creative. For example, this function has a point whose x value is 1. Therefore, 1 is part of the domain. This function has a point up here somewhere where the x value is -2, and therefore -2 is part of the domain. This function has a point somewhere way off to the left where x is -99, and therefore -99 is part of the domain. But you'll notice that this function has no point, for example, whose x-coordinate is 4, and therefore, if there's no point whose x-coordinate is 4, then 4 is not part of the domain. Now, I've given you 4 examples, three numbers that are in the domain and 1 number that isn't. There's no procedure here, but a little bit of thought and trial and error will eventually lead you to realize that if x is any number between -infinity through 3, and I'll remind you that the comma here in interval notation represents through, then there will be a point on the graph with that x-coordinate. But anything 3 or higher, there is no point on the graph that has that x-coordinate. You'll notice the parentheses by the 3 is the interval notation symbol for exclusion. So when we say -infinity through 3 and use parentheses at the 3, what we're really saying is all numbers from -infinity up to 2.999, so to speak. You can see that graphically here, that if x is any point in the green zone, there is a point on this graph corresponding to that x-coordinate, and that green highlighted interval is -infinity through 3, with the symbol of exclusion or the parentheses at 3. Let's talk range. Range is all possible y values in this function. Well, again, there's no procedure here, just sort of trial, error, and observation and cleverness. Watch what I mean by that. If this graph has a function whose y-coordinate is -2. This function also has a point whose y-coordinate is 3. This function also has a point whose y-coordinate is 7,000, somewhere way up there. But this function does not have a point, for example, whose y-coordinate is -5.3, so that would not be part of the range. And again, there's no procedure here, but if you work hard enough and think about it, about where all the y values to this function are, you'll realize that y can be anything from -5 up through +infinity. And you can see that represented by this green highlighting of the y-axis right here. Let's take a look at a very similar looking function with some actually different features here. First of all, this solid dot means that this point is part of the function. And this up arrow, which looks exactly like the other up arrow, actually has a different meaning when you combine it with this dotted line here. What that means is that the graph is getting closer and closer to that dotted line. It's called an asymptote. But it's getting closer to that line without ever crossing over the line or touching the line itself. Which means that while this graph does go up forever, it does not go leftward forever. So, let's talk about the domain of this function. Domain meaning all possible x values. This function has a point whose x-coordinate is 2.5. It has a point whose x-coordinate is negative 1.9, slightly to the right of that dotted line. It has a point whose x-coordinate is 0, but it does not have a point whose x-coordinate is negative 4. And again, there's no procedure for domain and range, but what one realizes eventually by just looking at where the function is there are certain x values that occur in the function, and there are certain ones that don't. After enough thought and cleverness and just thinking about it, one should come to the conclusion that this function has all values between -2 and 3 as its possible x's. Remember, the comma means through. The parentheses is the symbol of exclusion. Why are we excluding -2? Because the graph never reaches the dotted line. So there is no point on this function whose x-coordinate is -2. Why is there a bracket by the 3? The bracket is the symbol of inclusion, meaning, yes, there actually is a point on this graph whose x-coordinate actually is 3 itself. It's the solid dot. You can see the domain represented by this green shaded region here that goes from -2 through 3. If x is any of the numbers in that region, there will be a point on the graph corresponding to it. Otherwise, there won't be. And finally, let's take a look at the range here. The range of this function, again, is all the possible y values. And the possible y values are many. Let's look at some examples. There's a point on this graph whose y-coordinate is -5. There's a point on this graph whose y-coordinate is 2. There's another point on this graph whose y-coordinate is 2. But there's no point on this graph, for example, whose y-coordinate is -10. After enough thought and trial and error, you'll come to the conclusion that the possible y values of this function are anything that go from -5 all the way up and up to positive infinity, including the value of -5 itself. And you can see that the range is represented by this shading of the y-axis here, starting at -5 and going up to infinity. Now we're going to take a look at some domain questions that are not graphic. It's called implied domain. Every function has what's called an implied domain, which means if the domain isn't stated, there's still certain numbers x can or cannot be based on some rules of math. Let's talk about that. So in this particular function, you'll notice that we have a square root, also known as a radical. And one thing we know about radicals is that if you try to radical or square root a negative number, the result is imaginary and not real. So, for example, in this problem, we would not allow an x value of 11. Why not? Because 7 minus 11 would be -4, and then radical -4 not being a real number would not be considered part of the domain of this function. So what we have to do is think about domain as all possible inputs, or what are all the things that x could possibly be? Well, for example, x can't be -4. X can't be 4. So what we have to consider on this problem is what are all the things that x can be that won't cause the radicand, that's the thing under the radical, to be negative. Well, one thing you'll notice, and there's no math procedure here, but you'll notice that x would have to be a number less than or equal to 7 to avoid a negative radicand, which is if x were higher than 7, we would have a negative number under there. And so you can write the domain this way, which is pronounced the set of all x such that x is less than or equal to 7. But typically, interval notation instead is considered superior. So I'm going to write it as -infinity through 7. Remember, the comma means through, and the bracket means including. Why am I using the inclusion symbol at 7? Well, if you look at the original function, you'll see that 7 is a valid x value or input to this function. After all, if you plugged in 7, you'd get radical 0, which is 0 and is a real number. Here's a second example where we have to find the domain. This problem doesn't involve any radicals, but it does involve a fraction. And you may recall from previous math classes that in a fraction, the denominator could never equal 0, because then it's incalculable and doesn't exist. So on this problem, we have to avoid the denominator being 0. We can't choose any x values that make that happen. Those values turn out to be 5 or -3. And here is the algebra that led me to that conclusion. Hit pause if this seems unfamiliar to you. But once we've concluded that x cannot be -3, nor can it be 5, because either of those inputs would make the denominator 0, the conclusion therefore must be that x can be any number that isn't equal to -3 and isn't equal to 5. To say that in interval notation looks like this, which looks really strange. What you'll notice here is the union symbols in between the intervals. And let's talk about each of the intervals in this answer. -∞, -3 represents that x can be anything less than -3, but not -3 itself. Notice I've used the parentheses of exclusion there. The interval in the middle, -3, 5, represents that x could be any number between -3 and 5, not including -3 and not including 5. And the interval on the end represents that x can be anything 5 through infinity, but again, notice the exclusion symbol at 5 to say that x actually has to be bigger than 5. And here's our last example. This one's really tricky. First of all, it has a radical in it, and the radicand, the thing under the radical, is not allowed to be negative. And if the radicand can't be negative, that means x minus 5 can't be negative. The only way to guarantee that x minus 5 isn't negative is for x not to be a number lower than 5. So we know that x can't be lower than 5 because that would produce a negative radical, a non-real answer, and therefore that's not allowed. But remember, denominators can't be 0 either. And so the question here is, are there any x values that would make the denominator 0 and thus be an invalid input? Well, it turns out x can't be 21. I challenge you to hit pause and plug in 21 for x and see what happens. If you took me up on my challenge, you noticed that when you plug in 21 for x, the denominator is 0. And since that's not allowed, x cannot equal 21. If you don't see how I would have come up with that number, hit pause and check out this algebra, and you'll see why x cannot be 21. So, now that we know x can't be 21, and we had already concluded earlier that x cannot be any number lower than 5, it's logically consistent to assume that x can be any number 5 or higher except for 21. I could write that this way using set notation, but the more common way to write it is this way using interval notation. You'll notice the first interval here, 5, 21, says that x can be any number between 5 and 21, including 5. Notice I've used the bracket, the symbol of inclusion, by the 5. But notice I've used the parentheses or the exclusion by 21 because x can't be 21. And for the second interval, 21, infinity, you'll notice that I use the exclusion by the 21 again because x can't be 21, but it can be anything higher.